我还身上做回去写我俩。几天还在干什么？明天还。
Any questions from last class or homework? Second homework, you guys look at it. Hopefully a little easier. No. You forgot on your YLM, VJ coefficients. Not, yeah, you can come. Talk to me. Okay. The last class we had finished a discussion of what happens to a system. Remember, we had in the rotating frame and so I'm going to write rotating frame, right? And RWA. We had a Hamiltonian for the two-level atom interacting with electromagnetic field. So this was our Hamiltonian, where of course these states 2 we wrote down as rotating at the frequency nu, and 1 was the bare 1 state. So I guess technically these all have griddles on them, but I dropped the griddles, right? So this was our Hamiltonian in the rotating frame and the rotating wave approximation. And from this Hamiltonian, which we can write in matrix form as 0 minus omega star over 2 plus minus omega over 2 and then minus delta. This was our Hamiltonian, which if you recall I also said that this Hamiltonian is effectively looks like now the 1 twiddle and 2 twiddle states are separated by a detuning delta well, I guess if delta is greater than 0, then it's actually 1 twiddle is above 2 twiddle, and this is, delta, the spacing between 1 and 2, because now 2 is below the state 1 in this new rotating frame, right? This would be the equivalent picture from that Hamiltonian, and there is now driving term omega or omega star between the two states, right? And then we saw that if, for example, now if delta is the largest frequency in the problem, that is if modulus of delta is much, much greater than omega, but of course still keeping delta much, much lesser than nu, that satisfies the rotating wave approximation, right? And then we had two cases, red and blue detune, right? And do you recall what happens in the two cases? Blue and red detuning for far off resonance. So we had far off resonance. Oh, first of course I should point out that, you can just directly diagonalize the system, and when you diagonalize the system, for example, on resonance, then you get the dress states, right, which are completely mixed. Phi plus and phi minus, which is superposition of 1 and 2. And when they're off resonance, when delta is not 0, then you get some mixture of 1 and 2. And now we are looking at the case where, say, delta is far greater than omega, it's far off resonance, while still maintaining the rotating wave approximation. Then you remember that for, say, delta greater than 0, which is the blue detuning, what will happen to these states? 1 and 2. Right? This is more for the case where delta is small, right? Delta and omega are comparable, let's say. And now I'm asking for the other case where delta is far greater than omega, and what happens to blue detune? What happens to the states? Which way do they shift when they're blue detune? What happens to state 1? What happens to red detuning delta lesser than 0 to state 1? Anyone? Which way will 1 and 2 move in the blue detune case? You can look at your notes from last time. Everyone's waking up. 11 o'clock, should be awake then. Do you think back to when we talked also about the forces on atoms, right? This is the principle that affects the force on an atom. Maybe you can reconstruct from that to know where the result. Okay. Will atoms be repelled or attracted if they are in the ground state and you apply a blue detune laser to an atom? Will the atom be repelled from the high intensity state or attracted to the high intensity part of the field when you are blue detune? Binary choice. You have to decide one way or the other. How many people think it will be repelled if you are blue detune and you are in the state 1? How many people think that it will be repelled from the high energy state? How many people think it will be attracted to the high energy, high amplitude area of the field? Okay, you got to show your hands. How many people say in blue detune the atom is repelled? Raise your hands. No one. Okay. How many people think it will be attracted to the state? 1, 2, 3, 4, 5. Okay. So that means that the atom 1 or the state 1 will have to move down in energy, right? And the state 2 will have to move up in energy. If you are for it to be attracted to the high energy state, right? The atom wants to minimize its energy, right? So is that right? No. Okay, good. All right. At least you know that. So it's the other way, right? Okay, and how much is that shift? Now thinking, I told you you have to know this in the sleep. AC star shift. What is it proportional to? Omega squared. Somebody said omega squared over delta. Okay, good. Okay, good. So in the blue detune case, the atom will be repelled from the high intensity region, and in the red detune case, the atom will be attracted to the high energy state. Obviously, if you're in state 1, if you're in state 2, the situation reverses, right? And it'll go the other way. So that's actually another way in which people manipulate the potentials that atoms feel, by essentially using something else to transfer population from 1 to 2 and so on. So there's lots of neat tricks that people have invented with forces on atoms based on this effect. Okay, good. starting to wake up. Okay, so, and we also talked about adiabatic passage. I'll come back to it, as I said, in more detail, which is consider the same thing from a continuum of like far off red detune to far off blue detune, and you can sweep in between and you can cause the atom to be initialized from state 1 into state 2, which is another trick that we play. So at the very end of that class, I briefly talked about the Bloch sphere. So let's introduce that formally now. You may have seen this already in other classes, hopefully, right? So I'll just go through this pretty quickly. So the Bloch sphere is basically a visualization of the dynamics of the two-level atom when it's subjected to some electromagnetic field. And it will also prove to be very useful when we think about quantum information processing. So the north and south poles of the Bloch sphere are labeled by the states 1 and 2. So the north pole is state 2 and the south pole is state 1, right? So, and then we also have the superposition states, say 1 plus 2 divided by root 2, which is say along the x-axis, and this is the y-axis and this is the z-axis, right? And the y-axis is then the state 1 plus say I times 2 divided by root 2. Okay? So we can now define a pseudo-spin operator SZ, which goes as 2, 2 minus 1, 1. And Sx, which goes as 1, 2 plus 2, 1. You can see its matrix is going to be 0, 1, 1, 0 when I write it down in matrix form. And Sy is going to have the form minus I 2, 1 plus I 1, 2. Okay? So the eigenstates, and you can verify that these spins, pseudo-spin, which is constructed from the original states of the, or the original kets for the operators for the two-level atom, that they satisfy the spin angular momentum algebra. Sx, commutator Sx, Sy will be Sz, and so on and so forth in cyclic permutation. Furthermore, you can also verify that eigenstates of these operators will lie as will be of these spin operators Sx, Sz, Sx, Sy will be plus z, plus or minus z, plus or minus x, plus or minus 1. Where I can put a cat if you like, just to indicate that I'm calling it these states here, plus minus 1, plus 1, plus 2, these are plus z and minus z, for example, right? So this is plus z, this is minus z, etc. Okay? So in terms of these operators, our Hamiltonian, the old Hamiltonian that I just erased, can now be written in terms of this spin Hamiltonian, in the rotating frame and in the rotating wave approximation. This can now be written as let me actually write it up next. Forward space. In terms of these operators, we can rewrite our Hamiltonian as minus h bar delta over 2 Sz plus 1 unitary operator minus h bar over 2 real part of omega times Sx. And I'll give this as a simple homework problem. You'll get it in the next homework, that you can verify that this is indeed omega star. I have to verify this. I got to go back and look at the notes. Maybe that's wrong. I'll check it and let you know whether the star is here or not. Okay, that's what I have in my notes, but I need to check that out. Okay, this Hamiltonian. I noticed that this Hamiltonian has this 1 over here, right? This unitary, unit matrix. That 1 is a function of the fact that we chose our energy to be 0 at the point of the ground state 1. If I had chosen my energy to be 0 in the midpoint between state 1 and 2, that unit operator would drop out. I'd be left with only this h bar delta over 2, sz, sx, and sy. Okay. But anyway, this Hamiltonian which I'm not showing now, that the operator that we can re-express the dynamics of the 2-level atom, which we had written in terms of amplitude C1 and C2. Remember, for the state vector, so psi was C1 times 1 plus C2 times 2. This effective Hamiltonian leads to dynamics for the spin vectors now, rather than the coefficients C1 and C2. So this would be like a kind of Heisenberg picture evolution for the 2-level atom, that these operators will satisfy this expression where omega effective again, I'm not proving any of these statements. I will show you how to do that in the homework. How to do that in the homework. I'll lead you through the steps. So this is very nice because it gives you a geometrical picture for the state vector psi. Basically, we are saying now that the state vector is represented by a point on the Bloch sphere psi, okay, which is made up of 3 components, okay, whose projections on the x, y, and z axes are components of this pseudo spin vector. Okay, so psi and s. This is equivalent to now the pseudo spin vector psi, and s is equivalent to the state psi. Okay, that's what we're saying. So we can think about what happens to the system's evolution. Instead of thinking about the components C1 and C2, we can picture it in terms of the evolution on this Bloch sphere. Okay, and probably you all have seen this formalism before. So in any sort of dynamics, the state vector S will precess around this other vector omega effective. Okay, so if the state vector psi started out here, and let's say that I have some omega, which I can also represent as a vector in the same space. Omega has some components. The magnitude of those components is given by essentially the real part of the omega, the imaginary part of the omega on the x and y axis, and delta, which is the detuning from the atomic transition. Okay? So this is where remember I told you at the beginning that by controlling the amplitude, the phase, and the detuning of the electromagnetic field, we can make the state psi move all over the Bloch sphere. Okay, and that is this expression over here. And you can see now that on this Bloch sphere, essentially we will precess around this omega effective. Okay. So you should think of this as a 3-dimensional sphere, obviously. That the state vector will precess. So, for example, if omega effective is right along the z-axis, right? So, which means that there's only a detuning and there's no value, then you will see that the state vector will go in a cone essentially around the z-axis. Or if I had omega being entirely along the x-axis, okay, right, which means that you started out with some amplitude omega, right, and let's say the phase was 0, and we can make that we can control that. And then if initially the spin vector started along the north pole, right? Let's say in the state 2, then it will process, right, around this x-axis. It will process in a circle until, let's say, it hits the state 1, right, the south pole. And if you turn off the microwave or the optical field at that point, you have created again what I call the pi pulse, because your spin vector, the effective spin vector, went by an angle of pi around the effective Rabi frequency omega. So the effective Rabi frequency in this picture has 3 components determined by the amplitude, the phase, and the detuning. And in this case, I set the detuning to 0. So this thing entirely lies along the x-axis, for example. Okay. Any questions? So you can see that this block sphere has multiple purposes, or it represents the components of the state vector, but also you could choose to look at the amplitudes of omega x, omega y, and omega z along the same axes, and omega, as I said, they are given by the amplitude, phase, and detuning of this. Notice that the magnitude of this guy, the magnitude of the Rabi frequency, is going to be given by the magnitude of the Rabi frequency plus delta squared. So the effective Rabi frequency is determined by both the detuning and the amplitude of the optical or microwave band. Okay? And so at first you might think, oh, actually having a high detuning, right? So imagine that I had a high detuning, then actually the effective Rabi frequency looks higher, right? And that is true. It will look like it's an effective Rabi frequency that's higher, but then you will find that you cannot drive the transition all the way from 2 to 1. Okay, because if you have a strong component along the Z, of course there's no precession around that. If you started in the 2 state and you have a very large Z component, then of course the vector doesn't precess around that because it's along the Z axis itself. So the cross product basically vanishes. And therefore you won't be able to fully drive this down to the 1 state. So you will see, for example, if you have a way to monitor the amplitude of the state 2, you will see oscillations which are very fast, but they won't be very large in contrast, because essentially you're not going from 2 down to 1, you're just oscillating slightly around 2, which is what I was trying to point out earlier. Like you'll go in a cone very close to the north pole, basically. So as an example, so if I had, some omega which is large, right, it's high detuned, and has some x and y components as well, now the state vector will basically precess around this, right, like that. And so it will stay very close to the north pole. Okay. So you will see, and the rate at which you see these oscillations will be very large, because as you can see it's a very large vector still, but you're not achieving, say, Rabi oscillations, for example, which will take you from 2 down to 1. Okay. So this monitoring of the detuning and the amplitude and all this is very critical. Yes?
Yeah, so in case you say if we this drive is along z-axis, right?
Yeah.
This we only have the detune but no drive.
If you have no drive, then you can think about what happens to the state, right? If it's along 2, then nothing happens.
Yeah.
Okay?
Just saying when omega is 0 is like there's no.
It's funny. It's a funny situation.
Yeah,
it's effectively like you've just rotated into a different frame, but you have not created any dynamics on the probability, because effectively it's like going to a different energy scale, right? Remember, detuning is just the energy scale. So it would be like I just renormalize my energy scales by some amount. So everything looks like it's oscillating fast, but it's doing nothing to the probability. Right? Because probability, this is like changing, say, e to the I omega to e to the I omega plus some delta. Okay? So I just moved to some rotating frame that's different. So it looks like there is a phase accumulating on the states, but you have not changed the probability to be in that state. the probability remains the same.
That's more like a mathematical thing.
Well, actually, there is one way in which it can be useful. So when you want to do Berry phase experiment, for example, then it turns out that this is actually useful. Okay. So I don't. Okay. So what I do is, what we can do sometimes is, if we can have a resonant pulse and an off-resonant detuning, then this can come into play. So for example, I can start with a system in some superposition of 0 and 1. Okay? So let's say along the x-axis, right? And now I turn on a detuning. Even though there is no effective field, now I have caused some precession along the equator plane. Okay? Yeah? And so that can alter what's happening to the system. Okay? Yeah, you're right. So the case when you have just detuning and no amplitude is kind of funny, because it's like you've not turned on any microwave, so what have you done? Right? Yeah. So it's a system where, like, basically this thing will precess, okay, around the equator. And if everything is perfect, it'll just keep precessing. Right? Yeah. But that doesn't really affect the dynamics. It should stay constant amplitude or probability to be in the state 1 and 2 at that point. Yeah. So the trick comes when you do like something like Berry phase, where you can like now turn on a slow ramp and move the state adiabatically with you and move it around the Bloch sphere. So I'll come back to that when we do adiabatic theorem or something like that. Okay. All right. Yeah. Good question. Thank you. Okay. So now, actually, at this point, I'm going to make a connection to something we discussed in classical optics. Okay, when we talked about the susceptibility of a medium. Okay, so imagine now, instead of just having one two-level atom, you had a gas or a solid that consisted of like many two-level atom systems. Okay, independent two-level atoms. Okay, and we can write down now the susceptibility of this medium. Remember what the susceptibility is? What is susceptibility? Does anyone recall how we define susceptibility? What is the connection between, say, the electric field and some quantity in the medium, right? The medium is a set of dielectrics, two-level atoms, let us say. Then what do we want to calculate from this picture? The P. What is P? Huh? Polarization. Very good. So we want to calculate polarization. Polarization is nothing but the dipole moment, right? It's the dipole moment times the number of atoms per unit volume in the medium. So I'm making now a connection of this two-level atom that is exactly, so here's, so we're done with the whole Bloch sphere picture. So I'm going to leave it there. This is a good picture to keep in mind when you're thinking about two-level atom dynamics. Okay, and there are many tricks that people have played. Like there are books that are written about like how to manipulate the system into like various states, and then you can start thinking about like two different atoms, and now what do you do with them if they are both on the Bloch sphere, and so on and so forth. So there's a like whole. If you read an NMR textbook, it's basically like tricks about manipulating the spin vector in the Bloch sphere with NMR pulses. Okay. So you can now go read some of those textbooks and you'll at least understand the basic principle here of manipulation. And they are very clever. They've come up with a lot of sequences which we'll discuss in a little bit. But now I want to connect back to something that I had originally promised a little bit, which is, suppose I take a two-level atom, okay, and illuminate with a strong drive on resonance. Sorry, this is a two-level atom, gas or solid. Okay, let's say it's solid. Okay, so there are n atoms. Okay, n two-level atoms. So let's just say n two-level atoms, right, per unit volume. And what is the time dependent polarization? P. Okay, P of T is simply n, the number of atoms, times the dipole moment operator expectation value. Right? In quantum mechanics, this is how we would calculate the polarization. And therefore, this, of course, as we have said before, is connected to the susceptibility by epsilon naught chi times E. Okay? So we want to find the susceptibility chi now, which is a function of this dipole moment operator. So go back to the 1 and 2 system now again. We go back to the, instead of the block sphere picture, I'm moving back to the usual 1 and 2 picture. We are on resonance. Okay? So the dynamics is just simple Rabi oscillations, right? So delta is 0 in that picture that I just erased. So the detuning is 0. So we have a drive which is entirely along x or y axis. So we're going to get Rabi oscillations, which are given by these amplitudes now. And actually, I could have probably also shown you the same thing in the block sphere, but it's a little easier to understand, I think, this way. This we derived 2 classes ago. Okay? And now we need the expectation of the dipole moment operator. Okay? The dipole moment operator we also wrote down. I'll just write down the expression now. And so psi, the wave function, right, is just C1 of t times 1 plus C2 of t times 2. And the one thing we have to remember is that we are now in the bare basis, the basis that is not rotating. I'm making that transformation back because it's easier to connect to the lab frame, right? So mu, which will be the expectation of the dipole moment operator, psi, in the state psi, and psi itself is C1 of t times 1 plus C2 of t times e to the minus I nu t times 2. Remember, because we, in the original rotating frame, we removed this dependence on e to the I nu t by transforming to that new frame, so we put it back to go into the old lab frame, that is the bare basis of the Hamiltonian, of the atomic Hamiltonian. And now it's just some algebra. I won't waste time with that. You can easily do it. So you put this in here, right? And mu is the dipole moment operator. So you're going to have mu is equal to C1 squared mu 1 1 plus C2 squared mu 2 2 plus C1 star C2 e to the minus I mu t mu 1 2 plus C2 star C1 e to the plus I mu t and d mu 2 1. Okay, so easy to verify. And then we want to put in the things, and we're going to assume that this atom did not have any permanent dipole moment to begin with, so mu 1 1 and mu 2 2 are 0, and we're going to also assume that mu 1 2 is equal to mu 2 1 star. Okay, and these all will just vary depending on the on the relationship between the polarization and the driving field E naught. You know that E naught had some polarization, and I'm assuming that they are all aligned and real, and so on. You can alter all this if you want circular polarization or something like that. Okay, so from that, it's straightforward to find mu, which is just 2 times real part of, you will show this, is, I'm going to skip all the algebra, which is real part of e to the I nu minus omega t minus e to the minus I nu plus omega t times, maybe I want to leave it, brackets mu 1 2. Okay. Okay. So, oh, sorry, off. Okay. You have to show this to them, okay? Just by substitution and verifying this, etc. Easy. It's pretty straightforward. Okay. Hopefully this is an interesting result to you. Because what you see is that the dipole moment, and which remember, the dipole moment times the number of atoms in the solid or in the gas, there's some dilute gas or bunch of solids which are the dipoles are not dense, because if it's too dense then you have to take into account some corrections. If you may remember from your electromagnetism, you have to introduce some corrections if there is a very dense solid of atoms, but it's also a very straightforward correction. It'll just make it like depends on like the the Clausius-Mossotti relation. So I won't like waste our time. You can go back and look in your introductory electromagnetism textbook. This is essentially what I'm saying is that I've assumed this relationship without any corrections for geometrical factors and for the density of the solid and so on. So those corrections have to be put in if you're going to be very careful. But the end result is that this guy here, the dipole moment, is strongly oscillating with terms which are dependent on nu minus omega and nu plus omega. So that's cool, because it means that when I drive the system between 1 and 2, I basically have a in the new frequency space, it's as if I have sidebands. I put sidebands on the system, not at nu, but at nu plus omega and nu minus omega. Okay? Which is very different from what you would think if you had, say, a harmonic oscillator. Okay? If you had a harmonic oscillator which was being driven by some system, you would just expect that the harmonic oscillator will also oscillate at the same frequency, nu. Right? That's what we normally say when we have a forced harmonic oscillator and we apply some drive frequency nu to it. Eventually, it will also oscillate at the same frequency nu, with some small correction, okay, which is due to damping and pulling of the resonance, basically. Okay. But in a two-level atom, the system operates very differently. Okay. Now it has two frequencies, nu plus omega and nu minus omega. Okay. So it's oscillating with these side bands. So it's highly nonlinear. So polarization is oscillating. And so when I try to re-express it in terms of the original E field, notice that omega depends on E, right? Omega, remember, if you go back and look at your definition, is basically mu to 1 times E naught divided by H bar, right? So what I'm saying now is if I expand this, right, I'm going to have terms which are, say, 1 plus nu minus omega, that's linear in omega. But then I'm going to have terms that are nu minus omega whole squared and nu minus omega whole cube, and each of those is going to bring in a power of omega, which is the Rabi frequency, which also is linearly dependent on the amplitude E. Okay. So we see that if I were to think about the susceptibility, right, chi is going to be highly nonlinear. It's going to have many powers of the input pump field in it. So this is the original basis in some sense for like nonlinear optics. Okay? So this is how people started thinking about, why a system could start to respond nonlinearly. This simple two-level atom system is enough to explain a wide range of nonlinear optical phenomena. Okay? A strong drive of a two-level atom immediately causes nonlinear effect. So now if I send some weak probe field basically in to probe the system to find the resonances of the system, it will see a lot of nonlinearities. It will have a nonlinear susceptibility that it will be experiencing when it propagates through the medium. Okay? So this is the basics. I'm not going into the details. So you can come back to that later, or you can choose it as a term paper or whatever it is. This is the basic reason why a system of two-level atoms behaves differently than just some harmonic oscillator, right? And we can discuss this more in later classes. Okay. All right. So I wanted to introduce these two things. I feel like these are like making connections in two different directions. The block sphere picture makes connection to quantum information processing, right? And also gives us intuitive idea for what's going on in the two-level system. The geometrical picture is always nice, right? Then you can like think about the system without having to solve the equations every single time. That's what is nice about the block sphere picture. And then this little example that we just did in 2 lines essentially gives us a connection in the other direction towards classical optics, or rather, in this case, to classical nonlinear optics. Okay? Which may be something that many of you have not encountered in your regular electromagnetism courses. How many people have encountered nonlinear optics in your regular classical electromagnetism course? Okay, 1% has. Okay. Maybe you took it somewhere else. I don't think we teach that yet. Maybe we do, I'm mistaken, I don't know. And hopefully then, later on in the class, I'll give some more connections to the susceptibility and derive it for certain interesting situations. So that's a connection, hopefully, that to both types of people who are taking this class. I know some of you from Paytech's group are here, and you probably think about nonlinear susceptibilities a lot in your lab. Okay, I'm going to erase this, and we're going to now introduce a couple interesting techniques and also generalize the two-level atom to multi-level atoms. Okay. Any questions about this? It's kind of amazing, I think, that a two-level atom, simplest system you can come up with, already has all this rich set of phenomena that you can play. And I'm starting. So the first technique that we are going to introduce, once again, this has to go back to that off-resonant fields. Okay. Remember when we discussed the off-resonance fields for driving of the two-level atom? We came up with that address state picture, and we saw the red detuned and blue detuned situation, and the movement of the states, and the AC start shift. Okay. So that was when we diagonalized the Hamiltonian, right? We basically were able to diagonalize the two-level Hamiltonian in the situation where the electromagnetic field and the delta are present, because it's a simple Hamiltonian, and then we were able to look at limiting cases, on resonance, far off resonance, etc., etc. Now we want to consider an approximation technique for certain situations. This approximation technique is called adiabatic elimination. Very important technique in quantum optics. You'll see it pop up again when we do things like three-level atoms, master equations, etc., etc. Okay. So in many situations in these cases, we will be considering off-resonant fields, where the applied frequency, delta, of the field is far off from the resonance, but still satisfying the rotating wave approximation, where delta is far lesser than mu. So let's go back to the situation mod delta is far greater than mod omega, but delta far lesser than nu still for the rotating wave. Okay? And the trick, or the sort of the magic of adiabatic elimination is going to be that in the lowest order, first order, we can obtain the exact results that we got by first diagonalizing the Hamiltonian and taking the approximation of like for Dutune expanding, we expanded the eigenstates, we expanded the eigenenergies, and we did that. And it's simple for two-level atoms, but will become harder as you go to multi-level atoms or other situations. So this trick, let's go back to this case once again. I think the easiest way to explain the trick is to show you how it works, is to demonstrate it, and then I'll show to you why it actually works. Okay? So let's say you have a field delta which is tuned to some point which is far away from the state 2. Then in the rotating frame, once again immediately I write down the equations of motion. So at this point I have not made any approximations, I'm simply writing down the equations of motion. Okay? And the point is to recognize that this guy, delta now, which is far greater than omega, is the largest frequency in this mathematical problem. Right? So this is very large. Okay? And therefore when you solve this equation, for example, and I'll do a formal solution in a few minutes, you will find that this delta starts appearing in like denominators. Okay, just like when we did that counter rotating and rotating terms way back when we were discussing the validity of the rotating wave approximation. And it will turn out that the amplitude of therefore of C2 will be very small, okay, and the phase evolution will be very fast because delta is the largest frequency in the problem. We can think of C2 effectively as following whatever is going on in C1. Okay, C1, basically if C1 changes, C2 effectively follows whatever is going on in C1, okay, and it with some factor, with some prefactor. Okay, so let us do the trick, and then I'll show you why it works. So adiabatic elimination is this step right here, which is I'm going to set C2 dot equal to 0. Okay, this is of course in first order. Okay, which means if C2 dot is equal to 0 from this equation, then to first order, when I solve this equation, C2 of 1 in first order is approximately, just setting this equal to 0, is minus omega over 2 delta times C1. Okay? And this is what I mean, that C2 adiabatically follows C1, right? Whatever happens to C1, with some factor, C2 will follow that same relationship. Now what is going to happen to C1 now? I put this C2 back into this expression over here, the first equation. Okay? So C1 dot, which is what I want to find out because that determines the dynamics now of the entire system, is going to be just a simple equation, which is C1 dot is going to be approximately minus I omega squared divided by 4 delta times C1. And remember this omega squared by 4 delta? That was the AC start shift. Okay. So what we have seen is that, or if I solve now this equation, C1 of t approximately is C1 of 0 times exponential minus I omega squared over 4 delta t, which means that I have changed the phase evolution of C1, and I have therefore changed the energy of state 1. So energy of 1 is shifted by amount, and it's a positive shift because everything we took as minus signs, or e to the minus I is basically the rate at which we did the transformation, which means that the state 1 moves up in energy. Okay? So this is the AC start shift. We can go to higher order quite easily. Okay? So we go to higher order simply by taking the value, and I'll show you why this trick works in a minute, but first let's just find the higher order term. Okay, we take that C2 that we had just obtained and put it back into the expression for C1 dot. Okay, so let me erase. We have C2 of 1. Okay, let me actually show you here. Okay, so C2 of 1 is over here, which means C2 of 1 dot, right? So this implies C2 of 1 dot is approximately minus omega over 2 delta C1 dot. Okay? And since C2 dot is equal to I delta C2 plus I omega C1, I can put that over here on the left hand side. So, is it okay if I erase this? Everyone have this on their, okay. So I'm now going to higher order. Okay, so the first order solution is simply C1 is shifted by the energy omega squared over 4 delta, and C2 will adiabatically follow C1. Okay. The limits of this approximation will be pretty clear once I do this. Okay. So what did I say? C2 1 dot is minus omega over 2 delta C1 dot, and I know that C2 dot is also has to satisfy this expression, that is C2 1 dot is equal to I delta, now the second order term for C2 plus I omega C1 over 2. Okay, so I equate these two expressions. Minus omega over 2 delta C1 dot is equal to I delta C2 to second order plus I omega over 2 C1. And then C1 dot, once again, we know is equal to I omega over 2 C2. So this gives me minus omega over 2 delta and I omega star over 2 C2 to second order is equal to I delta C2 of 2 plus I omega over 2 C1. So now I can solve for C2 of 2 in terms of C1 once again. So I obtain, just carrying through the algebra now, C2 of 2 is simply approximately minus omega divided by 2 delta plus omega squared over 4 delta times C1. Okay? So that's the second order correction to that first order adiabatic approximation. And now I can expand this guy in the denominator. I can write it down as minus omega over 2 delta times 1 minus omega squared by 2 delta squared times C1. Okay. So far I've just derived the expression for you. I've not told you why it works. Okay? So it just seems like a magic trick, hopefully. Or maybe you already understand. But so it's not a magic trick, and we can explain that quite straightforwardly. But once, let me just make sure I don't mess up my order of my notes here. All right. So the basic physics or intuition for this once again goes back to the fact that this delta is very large. Okay. So if we can, so that what we are doing is basically we are saying we don't want to follow the dynamics perfectly. Okay? This delta is going to cause large oscillations or large changes in the probability in the phase of C2 because it goes as I times delta, but we don't care about this phase because effectively the phase leads to this renormalization of the energies. Okay? So what we're going to do is to find out the amplitude to be in C1 or C2 to calculate that, we're going to coarse grain the evolution. Meaning, we're going to take some unit of time, tau, to step through the equation, and this tau will be large compared to 1 over delta. Okay? So there will be many oscillations. So it will be large compared to that, but still slow compared to the overall dynamics of the system, which is governed by, say, omega. Omega has some shape, right? And that shape, we are assuming, the rise time and fall times of this omega are much slower, okay, than this 1 over delta time scale. Okay, and that's what we want to follow. We want to really concentrate on that and not worry too much about what is going on with this large phase delta. So we're going to coarse grain the evolution on some time scale tau, which is much larger than 1 over delta. This is the physics or the intuition for this adiabatic elimination procedure, and we can prove it formally by a very similar way in which we prove the rotating wave approximation. But before I go on, I'm sorry, I forgot to mention this. If you look at this expression, actually, omega over 2 delta is the first term, remember? Right? And that's what we had right here, omega over 2 delta, that's the first order. And then the second order is not really present. This is actually third order, right? Because omega over 2 delta times modulus omega squared over delta squared. This is actually third order in omega over delta. So that original expression I wrote down is actually good to second order. Okay? So that's a nice thing about this adiabatic elimination in this particular system. Two-level acting, okay? Is that you can just take this and this will be valid to both first and second order in this system. Okay, so now I'm going to formally prove this adiabatic elimination. Okay? Or at least give you a sort of understanding of why it sort of comes from.
Okay. Yeah, I figured.
I think that's all I'll have time for, so let me just go through that. So this equation, C2 dot, I'm going to formally integrate this equation. Okay? So C2 dot equals I delta times C2 plus omega, I omega over 2 C1.
Yeah,
okay?
no, I get it.
So to formally integrate it, I'll just, so let me erase the rest of this. Don't need it anymore. Remember the trick started with setting C2 dot equal to 0. So that's what we're going to try and show comes out of this approximation.
Yeah, you're right.
And I'll just briefly write this over here, which I think, you know, if I have any differential equation dy over dt plus some is equal to some ay plus f of t, then I can multiply both sides by e to the a t.
Oh yeah, because I think there's only
Right?
Yeah. So
and then I can show that this is just basically rewritable because of this relationship that you know, I can basically write this as d over dt of some amplitude, let's say y naught e to the at, etc. Is equal to, on the other side, a y naught e to the at plus f of t. Okay? Anyway, so let me just write down the solution. Okay. At some point, you can basically show by using this example that y of t can be written as integral t naught to t f of t prime e to the a t minus t prime plus y of t naught times e to the a t minus 2. Okay? So I'll leave that to you to show by using that integrating factor trick. Okay? So with that trick, then we apply that to this equation. C2 of t is formally now given by t naught up to t I omega e to the I delta t minus t prime times I omega over 2 C1, and these are all functions of t prime now, right? In this integral. dt prime plus the term C2 of t naught e to the I delta t minus. And remember, I told you I'm going to coarse grain the evolution, which means I'm going to choose t minus t naught to be some tau. So choose t minus t naught to be equal to tau, where tau is approximately, say, 2 pi over delta. Okay. So this term, in this last term here, is e to the I delta t minus t naught will be just 1, right? When I substitute. So e to the I delta t minus t naught is 1 approximately, right? This is again, I'm going to stop dropping these approximations. This is the adiabatic elimination approximation. Once I do that, this integral, right, the first, so I'm left with t c2 t naught plus tau minus c2 of t naught now, right, because I can take this c2 of t naught over to that side, okay, is approximately equal to integral t naught to t naught plus tau. And now in that e to the I delta t minus t prime, I substitute e to the I delta t naught plus tau minus t prime. And then inside the brackets, I still have the I omega t prime c1 of t prime over 2 and all this times dt prime. Okay, easy enough. The substitutions. And now we make more approximations. I'm going to say that I'm going to assume that this tau, which is equal to, because 2 pi, because 1 over delta is because delta is large, 1 over delta is small. So this tau, right, which is set as this coarse-grained time scale, is much larger than is much smaller than any time scale over which omega or C1 are going to change. Remember, I told you that. So if I assume that C1 of t prime is approximately C1 at time t naught, because the time scale tau over which this integral is being evaluated is basically very small compared to the time scale over which things are changing. So tau is far lesser than time scale of evolution over which C1 and C2 are changing, which also means omega also is approximately omega at time t naught. So then this integral becomes much easier. We don't have to deal with these guys. They can just pull them out of the integral. C2 t naught plus tau minus C2 of t naught is approximately I omega at t naught C1 of t naught divided by 2, and let's see. And I'm also going to divide by tau, because you start to see it's going to start looking like a derivative as tau becomes smaller and smaller on the left hand side, right? So I'm going to also divide by tau on the right hand side, okay? And then I'm still left with this one integral, t naught plus tau e e to the I delta t naught plus tau minus t prime dt prime. And it's very easy to show that this integral must be equal to 0 because tau equals 2 pi over delta. Okay? Just straightforward, just make substitution. And so you see then that this whole term is basically 0, right? This part is not approximately 0. This part is exactly 0 as tau is equal to 2 pi over delta, but the rest of it was by approximations, right? We got to that point by approximating that omega and C1 don't change inside that integral. Okay? And that's the result. So basically we have completely we have shown that as tau gets smaller, this derivative basically is going to vanish. So that implies therefore C2 dot of t is 0 as tau gets smaller, or rather as delta gets larger. So as delta gets larger and larger, this result will become more perfect. Okay? So again, the physics of this is that I've given up on solving the equations exactly, but instead we're going to do it time steps of this tau, basically. And over the time steps of this tau, as we showed in that when we first put in the strip, C2, the excited state, adiabatically follows C1 with some factor omega over delta. Okay? It's like a perturbation theory, except we're doing it more, in time evolution, more exactly. So when can we expect this whole thing to be true? We can already see that this will be good for things that vary slowly. So C1 whole squared, which is the probability to be in the state C1 or C1 itself, for example, right? Because C1 obviously does not have this term. I erased C1, but you remember C1 did not have any deltas in it, right? So C1, C1 itself, and then anything that does not depend on the phase of C2, because remember the phase of C2 is what is being adiabatically eliminated. Okay, we are neglecting any changes or corrections to the phase of C2. That is effectively like setting, like we talked about, this phase of C2 which is oscillating really quickly with delta is being averaged out, is being coerced in. Okay. So, but C1 and the probability to be in C2, these will be good. Okay. All right. The phase of C2, for example, the phase of C2, if you like, that is not going to be good in this approximation. Okay, so you can't really solve for that. Okay. So if you are ever interested in the phase of C2, then you don't want to apply this technique. Okay. Any questions? Adiabatic elimination? I'll give you some homework problem to make you feel more comfortable with it. Seems like a magic trick, but hopefully this derivation has convinced you that it's just essentially some kind of approximation to the dynamics on this time scale. Okay? Yeah.
This is a proof that C2 dot is 0.
Well, it's a proof meaning in an approximation.
In this
approximation sense that we can justify why C2 is dot is 0.
But when you actually want to solve the thing, you have to repeat.
Yes, so you just set C2 dot 0, get the first order solution, put it back, get the second order, third order, etc.
Right. So if we keep doing that, we can get even higher order.
Yes, but as I mentioned, you only can trust that expansion, adiabatic expansion, for things like C1 and C2 squared, and but you can't trust it for anything that has to do with phase terms in C2, for example. So you have to be careful when you do that. C1, on the other hand, you can trust because it is the one that's driving the dynamics. If you think about it in some other kind of intuitive way, 1 and 2 are here, and let's say you started with everything in 1, and you turn a highly off-resonant field on, C1 is not going to change that much. Okay? It's a perturbation theory argument. C2 will change, and what we are saying is C2 will change only by sort of approximately the amount that C1 changes with some factor. Okay? So you can almost think of this as also an equivalent to perturbation theory. Okay? And what this adiabatic approximation allows you to do, or adiabatic elimination allows you to do, is calculate those terms rather quickly. Okay? To calculate the corrections to C1 and C2 very quickly by this method, instead of putting it in and working through the all the other stuff. Yeah, working through these integrals, for example. Okay, I think I'm going to stop here for today, because the next thing I want to talk about is multi-state systems, and we will introduce at that point things like the bound to continuum transition and so on. So I'll start that in the next class.
High intensity, ultra strong.
Yeah. Yeah. Sure. Just give me a second.
Give me some second.
Yeah. Sure.
So for the question 2 we have this,
Mhm.
right?
Wait, which one now are we talking about?
Question 2. So
Oh,
this one.
yes. So compute the decay rate from 2p to 1s,
Yes.
for which you should use the dipole moment from the previous.
Right, I've done it.
Okay, very good. So you do need to calculate the final density of states, right? Which is going to involve the photon that's released, because when the atom goes from 2 to 1,